Hello, I'm Tyler Havner,
Name is Mel Perez.
and this is our senior design project for Fresno State, and our project is speech recognition using the Altera D2 FPGA board. According to the U.S. Census Bureau, 11 million Americans need assistance with everyday activities, and 3.3 million use a wheelchair. For these Americans, simple tasks such as turning on a ceiling fan or opening and closing a door become a chore. And for this reason, there is a need for voice recognition in household devices to make for a hands-free environment. Our proposed solution is to employ an FPGA servo motor and a DC motor to control a door and ceiling fan. This would alleviate a lot of the day-to-day struggles that these people deal with. And some of the limitations of our project would be speaker dependence. So it would be mainly for just the homeowner, and the system would have to be trained by each user. And we're also relying on single word recognition, not continuous speech. And the theoretical concept behind our project is that a bandpass filter bank can expose the significant frequency content spectrum, and the human voice can only produce signals up to about 10 kilohertz. And as you can see by the plot, the human here has a nonlinear response to amplitudes. And for this reason, we can create a logarithmically spaced bandpass filter to save a lot of space. And our design path for this project, since frequency and analysis and DSP is very difficult to grasp in the time domain, we plan to use MATLAB as a proof of concept to kind of plot everything and see what it's going to look like in the frequency domain. And so we'll create a MATLAB model of our project and use it to simulate and test our thresholds and refine our project. And then from this MATLAB file, we can convert it to C and implement it on the D2 board.
So we're using the analog to digital converter that's embedded in the G2 board. It has a module named Wolfson WM8731 quarter, and it has both a left and a right channel for stereo sound. But since we're using human speech, both the left and the right channel are the same, and we're only using the left channel. It has a 24-bit resolution, and it's in 2's complement form. Um, this is how it's on the very bottom. You can see how each value is organized. So the MSB is the furthest to the left, and the LSB is furthest to the right. Okay, since it has a 24-bit resolution, we don't need that high of a resolution, and it would take up too much memory, so we decided to downconvert it to a 12-bit resolution. This gives us a 4096 possible quantized levels ranging from negative 2048 to 2047. And the figure on the left shows an example of a 3-bit A to D converter. It's divided into 8 different quantized levels, as you can see on the left side. It goes from 0 to 7. And the figure on the right side shows how you would downconvert from a 3-bit A to D converter to a 2-bit. So basically you just shift the bit to the right by 1, and that would give us a resulting 2-bit A to D.
The first step to our system is detecting the start of the word. In order to do this, we take the absolute average of two windows, both of length W, and then take the difference of the two and compare that to a threshold. And if it's greater than the threshold, then we've successfully detected the beginning of the word. And if not, then we continue on and continue to loop until we reach the end of the array, at which case no word would have been detected. And in order to counteract the effects of the mouth, that it's usually with speech, there's a negative 6 dB spectral roll-off just due to the effects of the mouth acting as a low-pass filter. And so in order to counteract that, we implemented a pre-emphasis filter, and it helps to just attenuate some of the lower frequencies and amplify some of the higher frequencies, since in speech usually the spectral energy is concentrated in the lower frequencies. And in order to calculate the cutoffs for the FIR filters, we used the equations on the left, and we used a logarithmic growth function of about 1.45 and an initial bandwidth of about 300. And using MATLAB, we calculated the B coefficients for our difference equation, and we ended up with the FR filter bank pictured there. And in order to generate our fingerprints, we used a 16 kilohertz sampling rate. And since all of our words were fairly small, we just took 8,000 samples. And kind of a good estimation of voice is using windows of about 10 milliseconds to 30 milliseconds. So we added we added the outputs of the squared of the filters. So we basically squared the outputs of the filters and then added those to an accumulator, and after 160 samples, we saved that as a point for the fingerprint, thus giving 100 points for each filter and 500 points total for each fingerprint. And as we're training the system, we would go through 3 samples of the word, and then all those fingerprint points would be added together and averaged.
Okay, so we have our comparison function, which would compare the incoming word to one of the reference fingerprints. Okay, so if it matches to any of the words, it depends. All the Q values represent one word, and all the P values represent another word. So it subtracts the values and then squares it and takes the square root of it. And then depending if the difference is within the threshold value, it would detect either whichever word is closest to the threshold. So, and then if there's no match, then it will display the message on the LCD that says no match.